All right. So, as I mentioned in my note yesterday, nobody ever did ask any questions on this review, so I'm not sure if everybody get it and felt really good about it, or just didn't ever really get it done. First set of questions were just evaluating limits, and remember, there's a number of different ways that can happen. Algebraically, the ones we really like are the ones that are continuous, like number one, right? It's just a quadratic equation. It'll be continuous everywhere. So it really doesn't matter what x is approaching. In this case, it looks like we're approaching 5, but we don't really care because no matter where it is, it's continuous. We can just plug 5 in. We really like that kind of problem. Even though this is a rational function, and there may be some issues down here which create discontinuities. Um, in fact, it looks like -1 would be a double root. In that case, 3 is not a problem. So that one's another one we could just do with substitution. But eventually you're going to start getting into some of these problems where you're going to have to use either some algebraic, like here we would want to um, distribute and then simplify. Here I think we'd want to factor and then simplify. On these two right here, with the trig functions, we want to remember a good friend of ours, this little guy right here. Uh, you can't ever do this one by substitution, but we know that the sine of kx over kx, sx approaches 0, not in general, but sx approaches 0 is equal to 1. Now remember, like sine of 5x over 5x is never actually going to be equal to 1. But the limit as it approaches 0 is. So just a couple reminders there. Um, Now these look similar, and yet they're not. These are more infinite limits. Either x is approaching infinity, which will become, an end behavior problem. So here's a right end behavior problem. That's a right end behavior problem there, right? Or the y's are approaching infinity, such as with, this guy right here. We're approaching 2 from the right. So what is going to happen? We can kind of take a look at what the graph would look like. Oh, it looks like from the right we're going down to negative infinity. We usually have a big discussion when we're doing this in class because, if you don't have a calculator, which this test is not a calculator test, it's supposed to be, then, the functions tend to be a little more simple on the test. Things that you can do with simple transformations, like, oh, I know what this 1 over x looks like. So if it's just moved 4 units to the right, I can predict what that's going to look like. But what if you did have an x on top and an x on the bottom, and then we talk about taking a point on one side or the other. In this case, it's the negative side coming in from the left. So what's happening? Are we going up or down? And by just plugging a number in, you don't need specific values, but you can just plug a number in and determine if you're going to get a positive or negative value. In this case, look, a positive divided by negative is negative, and you can see negatives indicate probably negative infinity is the direction I'm going to be going. So you wouldn't have to worry about that because I would assume you would just be using your calculator at free will. Um, Interpreting graphs, you did a whole lot of this type of thing on your limits quiz number 1, on your limits quiz number 3. Um, just knowing the different types of discontinuities, jump discontinuities, removable discontinuities, and how those are affected with whether limits exist or not, what the limits are. For example, the right limit as we approach 1 is a height of 1. The left limit as we approach 1 is a height of 1. Because the limits are both 1, we have a limit. The limit is x, approaches 1. I guess we would just call it f of x, right, is equal to 1. Even though the point where the function's actually defined is not there, the limit still exists. Very important ideas to keep track of when we discuss limits and whether they exist or not. This is the same kind of problem. It's worked out in your solutions pack, but this one you had to draw yourself. You had to draw the piecewise function. 21 was already drawn for you, so you're just interpreting what you see. Um, when it says where is the function continuous, it's probably going to be continuous at infinitely many values. It's easier to figure out where it's not continuous and then describe and then take those values out of the rest of the domain or intervals that are describing the domain. That's the easiest way to kind of answer that type of question. This is another one, piecewise function. You had to draw and discuss the types of discontinuities that you have. Once again, it's worked out in the course pack for you. This is one that asks you to identify types of discontinuities. You will not see any oscillating discontinuities, so don't worry about that. But removable jump and infinite discontinuities you have to understand well. And one thing you don't want to get confused with is the graphical features which cause the discontinuities and the discontinuities themselves. So for example, it looks like at 1 here, I'm going to have a removable discontinuity, and at 3 here, I'm going to have an infinite discontinuity. The infinite discontinuity is caused by the vertical asymptote. So at x equals 3, there is an infinite discontinuity because of vertical asymptote. But don't say the vertical asymptote is the discontinuity itself. For example, hole is not a defined as a type of discontinuity, but it causes removable discontinuities. Semantics in some degree, but you got to be careful about that. 24, just using properties of continuous functions, primarily the composite functions of continuous functions make new continuous functions. We did talk about that a little bit, but I don't think we ever saw that on the quiz, so maybe you don't need to worry about that too much. These are great problems where you really have to understand what you're seeing up here, so you know whether the function is going to be continuous, or maybe it's just a hole there, or maybe it's a jump. What's happening. And these are good. Um, Examples of the answers are in your course pack, but because you can't graph on the type of quiz you'll be taking on Google Quiz, probably don't have to worry about those types of questions. Repairing removable discontinuities. Remember, removable discontinuities can be removed. They're the only types of continuities that can be removed, right? And so we're looking for holes that create those. And so a lot of factoring is necessary. Know all your types of factoring. Difference of cubes, sum of cubes in this case, trinomials and the binomials, trinomials and the binomials, difference of squares, factoring out common terms, factoring by grouping, a whole bunch of different ways. But what you want to do is you want to identify the removable discontinuity by finding the hole, -4. That's going to be a key feature because the original graph will be good except at that hole. Okay, and to remove that discontinuity, we're going to say when x is 4, here's the y value. We're going to plug the hole. How do we do that? Well, just like we did back in Unit 1, we're going to go to the reduced equation and evaluate that at the location of the hole. Okay. Here's another example where you just got to have to know how to factor, right? And once you do that, you know, oh, there's a problem at 1, there's a problem at -1. One of those discontinuities is probably going to have to be here. Which one canceled? Oh, it was 1. 1 was the hole. That's the one that created the removable discontinuity. Now, go to the reduced equation, which I think would just be that dude right there. Plug your value in to find the missing value. And then we finally got to Unit 2.4, which we just got done taking a quiz on. Rates of change, average rate of change. Don't just assume you have to use a difference quotient every time. If you see the word average, slow down and just we know that x1 and x2 are 2 and 5, so find f of x1 and f of x2, or y1 and y2 by plugging the numbers in.
You're not going to have any free response on this one, so some of you guys that like to cut work, I guess you could do that, but it's always safer to work things out. Here's that average rate of change formula that we like to use, f of a minus f of b over a minus b, or f of b minus f of a over b minus a. All right, now we get into the slope of a curve, or the equation, or the slope of a tangent line, same thing, right? Instantaneous rate of change, same thing. This is where we have to use our limit as h goes to 0 of f of a plus h minus f of a over h. And these are worked out in the course pack, and nobody asked any questions on them, so I don't work them out. They are worked out very thoroughly in the course pack, but make sure you know how to do that. That's what the quiz you just got returned to you was on, and I would say overall most of you guys did really well. A couple things not showing work here or there, which is always going to be the case. Just be a little more thorough, but for the most part, I thought people were pretty good shape on using the difference quotient. Same idea with the difference quotient here, but this time it's an application problem. So we set up the equation of free fall from a tower, and then we use the difference quotient. And once again, this one's worked out in the course pack probably a lot neater than what you see there. Same thing here, same type of question, right? Here's that general formula where you do h naught minus kt squared, which is the initial height, minus the rate of fall, where k is the gravitational constant, depending, I guess, on what planet you're on. So in this case, they said that we were on Mars, so it's a smaller constant, 1.86, than you would have on Earth, because Mars has less gravity. Smaller planet, no atmosphere, but mostly because it's a smaller planet. Anyway, not no questions, so I really didn't have anything to focus on, so I just tried to give you some general ideas. We did cover a lot of information this unit, and boy, it all had to do with limits at some point, so I hope you understand what limits are, when they exist, how we can use them to help define horizontal asymptotes, vertical asymptotes, and behavior, how we use the idea of a limit to get a really strong definition of what continuity, and when continuity exists and when it doesn't, for the two things that have to happen for continuity to exist, and then how we use limits to help find something that we could never do with algebra, which is the instantaneous rate of change of a curve, or the slope of a curve at an exact point. Um, Something that really bridges algebra into calculus. Good luck on your last quiz on Unit 3, and have a good weekend.